Okay, good morning. This is our eighth lecture for the course Compressible Flow and Gas Dynamics. If you recall from the last lecture, we have started our discussion on the speed of sound. Okay, and while doing so, what we have done, we have considered a sound wave, and then we have assumed that fluid is there on the ahead and downstream of the sound wave, and then we applied continuity momentum equations. Okay, and with the help of these equations we have tried to establish the relations for the sound wave, and we have come up with one of the relation as A equal to del p by del rho at constant entropy. One is this relation we have got, and second, if you see, we have done some manipulations and then we found A can also be related to the isentropic compressibility of the fluid, and we obtained A is equal to specific volume per unit beta s. Okay, so these two relations we have seen in the previous class. Now let's impose one more condition over here. The first condition is that now we have a thermally perfect gas. Okay, so first condition is I will be considering the thermally perfect gas, and second important point is while variation of pressure and density is taking place with the propagation of the sound wave, that is nothing but an isentropic process. Okay, so if we see for a thermally perfect gas undergoing through isentropic process, we have got one formulation that PV power gamma equal to constant. So that is something which we have already obtained for thermally perfect gas for an isentropic process, means for an reversible adiabatic process. Okay, now what I can do over here, I can write this P is equal to C divided by V gamma. So 1 by V will become nothing but rho. So I can write it rho times gamma over here. Now you have pressure as function of the density, and this is valid nothing for isentropic process. So I can now calculate this del P by del rho derivative. Okay, so if I do so, I will get del P by del rho at constant entropy is equal to C times then derivative of this rho will become gamma times rho gamma minus 1. Okay, and C I can replace with PV power gamma, and V I can write divided by rho gamma. Okay, so C I have replaced with PV gamma, and where V I have presented in terms of specific volume times gamma rho gamma minus 1, and from here if I see this rho gamma will cancel, and I will end up in getting gamma P divided by rho. Okay, so this is my formulation. One important point I missed over here, this is nothing but A square. Okay, in place of A, this is A square. So from here I can say that my A square for thermally perfect gas is nothing but equal to gamma P divided by rho, and from here we will get A as nothing but my square root of gamma P by rho. Okay, so this is one important relation, but remember that isentropic over here is not an assumption. For sound wave the process is always isentropic. Okay, however this thermally perfect gas is the assumption over here, so we are considering this process particularly for a thermally perfect gas. Okay, now what I know for a thermally perfect gas, that PV is equal to RT as well. Okay, so from here I can write P by rho equal to RT. So I can also write my equation for the sound wave as gamma, sorry, square root of gamma RT. Okay, so now if you consider your air at standard conditions, Okay, so if we consider the air standard conditions, particularly the cold air standard assumptions, then as per that, we will be having gamma equal to 1.4 for air, okay, and temperature will be equal to 298 Kelvin, okay. So these are the air standard conditions. So corresponding to these air standard conditions, and we know that characteristic gas constant for air is 0.287 kilojoule per kg Kelvin. Okay, so if we do substitute these conditions for air at standard conditions, we will get speed of sound becomes 340.9 meters per second. So this is an important result. Okay, so majority of the time we use this number, okay, because we are considering in majority of our discussion on compressible flow medium to be air. So for this air, if we consider the standard conditions, then we get speed of sound as 340.9 meters per second. Okay. Now, so ultimately we have to go for the analysis of the shock waves. Okay, but before we are going for the analysis of the shock wave, there will be some important relations which will be actually useful while we are trying to derive the fundamental idea or mathematical analysis across the shock waves. Okay, so let's try to see certain alternate forms of energy equations which will be very useful while doing the analysis for normal shock waves. Okay, so we will now see some of the alternate forms of energy equation. So we know that for one dimensional system, because in normal shock wave we will come across 1D flow. For 1D flow, our energy equation is nothing but, please tell me what is the energy equation for 1D flow? H1 plus V1 square by 2 equal to V2 square by 2. Okay, so this is my energy equation for one dimensional situation. Now if I consider the assumption of a calorically perfect gas, what will happen? For a calorically perfect gas, Cp and Cv are constant. Okay, so now I can simply write that my dH is equal to Cp times dt. Okay, now if we consider that at absolute zero temperature my reference is such that I have zero value of enthalpy. So this is my temperature in Kelvin. So at absolute zero temperature, what I have, I am saying my enthalpy is 0, and similarly my internal energy is also 0. Okay, so if I have to calculate, say, enthalpy at this point 1, obviously I will be referring with reference to this 0 Kelvin. Okay, so I can say that H1 minus H at reference state H0. Okay, or let me, because later on I will be using this O for stagnation property, so let me write it in the superscript. Okay, so say this is H naught at reference state, that I can write as simply equal to Cp times, if this is my temperature T1 and minus 0 Kelvin, and H0 is 0. So ultimately I can say that for a reference point, common reference point if I take, then I can write H1 is equal to nothing but Cp times T1, considering that absolute 0 is my reference state having enthalpy 0. Okay, so now this H1 I can simply replace with Cp times T1. However, this replacement is applicable, so till now this energy equation is applicable for any type of fluid. Once I put this approximation, now this equation will be valid only for calorically perfect gas. Okay, so once I take the assumption of calorically perfect gas, I can write that Cp times T1 plus V1 square by 2 equal to Cp times T2 plus V2 square divided by 2. Okay. Now let's divide throughout by Cp. If I divide throughout by Cp, I will get T1. Okay. Let's now do that. If you recall, in one of the previous lecture, we have also presented Cp as nothing but equal to gamma R divided by gamma minus 1. Okay, so let's replace Cp with gamma R by gamma minus 1. So if I do so, I will get gamma R T1 divided by gamma RT2 by gamma minus 1 plus V2 square divided by 2. Okay. So now what is gamma RT1? Speed of sound for condition 1. Okay. So this I can write as speed of sound whole square, because square root of gamma RT is actually speed of sound. So what I can do, I can write this thing as A1 square upon gamma minus 1 plus V1 square by 2 equal to A2 square by gamma minus 1 plus V2 square by 2. Okay. So this is nothing but the another variant of energy equation, and this variant is involving formulation of speed of sound. So you have presented now the same energy content of the fluid medium, but in terms of the speed of sound. Okay, so this is also one important relation which we will be using many times. So let me number it, say equation number 1, because this will be useful many times during our subsequent discussion. Okay, now now before just trying to find out some more variants of this, let's see one interesting aspect. Say I have flow field. Okay, I have some flow field, and in this flow field, say this is my point number A. So here I will be having some velocity vector which is tangent to the streamline, and whatever the point over here is, say this is my point A in the flow field. Obviously when flow will further progress, then I will be having some another velocity vector over here, and say this is my some another point B in the flow field. Okay, so now at point A I will be having certain flow velocity V, and corresponding to these conditions of the, say whatever medium we are having, this medium will have certain speed of sound A also. Okay, so corresponding to this, I can define my Mach number as V by A. Okay. Now this Mach number can have any value. It can be less than 1, it can be greater than 1. Now what we want to do, we want to create one hypothetical situation so that if my Mach number is less than 1, then I will accelerate the flow adiabatically such that at point A my Mach number becomes 1. Okay, is this point clear? So what I am saying is, if Mach number is less than 1, I want to adiabatically speed up the flow such that Mach at point A becomes 1. Okay, this is what I want to do. Okay, so say initially when this Mach number is lesser than 1, then obviously here I will be having, say, certain temperature of this medium at point A as T. Fine. So when I will be doing this adiabatic speed up of the flow, then what will happen? I am investing something. Okay, so it means that thing will alter nothing but the temperature at this point. because if you are doing adiabatic if you are doing only the acceleration and then whatever amount of heat is generated because of that acceleration, that if you are rejecting out of the medium, then it can sustain at temperature T. But if you are not allowing any heat transfer to take place but only doing the some adiabatic process, okay, which is actually changing the speed of the flow, ultimately what we are doing, we want to make Mach number equal to 1, so it means we are changing the speed of the flow. So in that process of changing the speed, basically its temperature will also change. Okay. Similarly, if my Mach number is greater than 1, then I will do adiabatically slowing process till Mach number is becoming 1. Okay. So what I am saying now, that when I was having some condition in the flow field, and with this condition I was having some value of Mach number and say T as corresponding temperature. Now I am trying to consider some situation where I have adiabatically either accelerated the flow if my Mach number is less than 1 in order to bring it to Mach number 1, and if Mach number is greater than 1, then I have slowed so that it becomes 1. So in both the processes I will be having change in temperature of the fluid medium. Okay, and say T star is the temperature of the fluid medium once at point A Mach number has become 1. Is this point clear? So corresponding to this T star, my new speed of sound A star will be nothing but equal to gamma R T star. Okay, and similarly we define one Mach number which is called as characteristic Mach number. And this characteristic Mach number we represent as m star, which is nothing but equal to V divided by A star. Okay. So characteristic Mach number is something which is V by A star. Now later on we will find the application of this characteristic Mach number, because when we consider the situation of supersonic or hypersonic flows, we say that Mach number is greater than 1. However, there is no highest limit for the Mach number. Okay, so in certain situations I can have highest limiting value of the Mach number as Mach number approaches to infinity. So under these conditions we will see that this m star will have some finite value of the Mach number. This characteristic Mach number will become finite, and we will be able to deduce some of the features regarding the flow characteristics. Okay, so that is the reason this will help later on. So the point is clear, we are not doing any change over here, but what we are doing, we are hypothetically considering in our mind, if we adiabatically accelerate or deaccelerate the flow, then ultimately my temperature will change such that finally we are reaching to a Mach number of 1. So corresponding to this new Mach number, a new temperature condition, whatever speed of sound we are getting, if we divide flow velocity with that speed of sound, then we get nothing but our situation of characteristic Mach number. Okay. Now one important aspect is that this adiabatic speeding up and adiabatic slowing process I am restricting only up to point A. Okay. So this characteristic Mach number I have specifically defined at the moment for point A. Okay. Now I cannot say that from A to B also flow has to be always adiabatic. So from A to B flow can be of any nature. However, if from A to B flow is adiabatic, then automatically we will get a situation that A star at point A will become equal to A star at point B. Is this point clear? Okay, let me explain again. So what I am saying is that first thing you have to remember is whenever we are trying to obtain this A star, we are not saying that my complete flow field is adiabatic. Okay, so I have considered the situation that only at point A I am adiabatically accelerating or slowing the process. So that is specifically designating at point A. From point A to point B, flow can be of any nature. Okay, so if from point A to point B the nature of the flow is not adiabatic, then my, okay, first before that, likewise I have defined A star at this point A. Similarly I can define A star for point B, because point B will also be having some Mach number situation, and there also I can consider some T star at which Mach number becomes 1. So I can define some situation of A star for B also. Okay, so that will be independent. So say I have defined some A star B, and here I have defined some A star A. For defining A star condition I only need T star. That's it. Okay. Now the point is, as I told, that this particularly star parameter is specific to a point in the flow field, and it is not having anything to do with the complete flow field. Okay, so this formulation is applicable for any type of flow field. Okay, it is not specifically only for adiabatic flow field. So when this situation is applicable for other than adiabatic flow situation, then my A star A will not be equal to A star B. Okay, why it will not be equal? Because A star concept is coming from the adiabatic acceleration and deceleration of the flow. So if my flow from point A to point B is not adiabatic, in that case whatever value of A star I will get at point A and whatever value of A star I will get at point B, these two will be different, because initial temperature condition at this point and at this point may be different. Okay, on the other hand, if I consider that my flow is adiabatic, okay, if flow is adiabatic, then whatever speeding up and slowing down process we are doing, okay, that temperature change from this point to this point will be actually accounted in overall effect what we are making at point B. Okay, so this is the reason that value of A star at point A will be equal to value of A star at point B if my flow field is adiabatic. So this is for adiabatic flow field. Okay, now this is one important point we will be utilizing later on. This value of A star equal to constant for adiabatic flow field. This is an important result which we will be using later on in while doing the analysis, particularly for the shock waves. Okay. Okay. After this, we also define one very important set of properties in compressible flow, which are known as stagnation properties. Okay, so if you do recall, then we do talk about stagnation properties in our fluid flow, or say thermodynamics, basic thermodynamics course also. So can you tell me what do you mean by stagnation property? What is the meaning of stagnation property? Say you are at point A. Here you have some enthalpy H, pressure P, temperature T, velocity V. Okay. Now, if you isentropically slow down the process such that finally it becomes stagnant. So, what we have to do? We have to do isentropic slowing process till it becomes stagnant. Okay, that is the situation. So we have to make the flow stagnant. So in this process, what will be happening? Ultimately, my velocity will become 0. Okay, and corresponding to this stagnation point, whatever the pressure and temperature condition we are having, these are known as stagnation or total pressure. Similarly, stagnation or total temperature. Okay, whereas the pressure and temperature at this point A are known as static pressure and static temperature. Is this point clear? So what I am saying is that I have some point, and from this point, if I isentropically slow the flow such that finally it reaches 0. So what will happen? This flow was having some kinetic energy. Okay, what you are doing? You are trying to isentropically change this kinetic energy to finally the 0 situation. Okay, so ultimately that kinetic energy change will be reflected in terms of heating of the fluid medium, and if it is heating the fluid medium, then ultimately what is happening? Its molecular motions are actually changing, so it will result in overall increased pressure and temperature conditions. Okay, so that's the reason these are represented as nothing but the stagnation or total pressure and total temperature condition. Whereas at this point, when the kinetic energy is separately participating as the bulk motion, okay, it is not contributing into the molecular motion. Okay, when I am saying V over here, then V square by 2 will be my bulk kinetic energy. I am not talking about now the molecular kinetic energy. I am talking about the bulk kinetic energy. When bulk kinetic energy is not included in our pressure and temperature, then these are we are calling these as nothing but the static pressure and static temperature. So typically the stagnation properties are represented by subscript 0. Okay, so I will be using say P0 and T0 as the stagnation pressure and temperature. Okay, or say if enthalpy I have to represent, then I will call it as H0. Now let's try to see what will happen as per the energy analysis. So from energy concept I can say that H plus V square by 2. Say this is the situation before stagnation, and after the flow is isentropically made stagnant, then my enthalpy will be say H naught and velocity will be 0. Okay, so from here once again for calorically perfect gas, Cp times T plus V square by 2 will be equal to, this will be equal to Cp times T naught. Okay, so from here I can say that let's divide throughout by Cpt. So I can say that T naught by T will be equal to, T naught by T is becoming what? 1 plus V square by 2Cp. Is this one clear? So now okay, so now this is the, if you are having any temperature condition corresponding to that temperature, you are having certain velocity of the flow also, you can calculate the value of corresponding stagnation temperature. So it means that in your flow field, if you are at point A, at point B, if at point A temperature is TA, if at point B temperature is TB, then you will be having some different stagnation temperature corresponding to this, some different stagnation temperature corresponding to point B. However, if the process, this complete process is nothing but isentropic, okay, if my flow field becomes isentropic, then what will happen? Stagnation, pressure and temperature will become same for both the points. Okay, is this point clear? Now let's further try to little bit modify this equation so that I can present this equation in terms of the Mach number, because ultimately whenever we will be dealing with the compressible flow situation, we have to represent everything in terms of the Mach number. So Mach number is actually the ultimate thing. Okay, so let's try to see that in terms of Mach number how I can represent it. So T naught by T will become 1 plus V square by 2 times, and then I will replace this with gamma R by gamma minus 1. So this will become from here that T naught by T equal to 1 plus gamma minus 1 divided by 2, and this gamma RT will become A square, V square by A square will become Mach number square. So another important relation. So now you can see your stagnation parameter is for a calorically perfect gas is nothing but depending upon the value of gamma and Mach number of the flow. Okay, so obviously temperature situation should be known to us. Now we also know for the thermally perfect gases that P naught by P equal to rho naught by rho gamma equal to T naught by T gamma by gamma minus 1. How we are getting this equation? If a calorically perfect gas goes through isentropic process, then we say that process is reversible adiabatic, and if we make entropy 0, then we have obtained these important relations. PV power gamma equal to TV gamma minus 1 equal to constant, P gamma T power gamma minus 1 equal to constant. Okay, so from these three important relations which are applicable for an isentropic process, we can write this formulation. Okay, and whenever I am dealing with the stagnation properties, what I am saying that I am at point P, T and V, and then I am isentropically slowing down the process till I am reaching to point P naught, T naught and 0. Okay, so this whole process from given condition to reaching the stagnation properties is nothing but an isentropic process. So for an isentropic process involving the calorically perfect gas, I can write these equations. Okay, so this equation I have already dealt you previously. So from this I can represent that my rho naught, or say first let me write P naught by P will become T naught by T power gamma by gamma minus 1. So what is T naught by T? 1 plus gamma minus 1 by 2 Mach number square. Okay, and this whole power has to become gamma by gamma minus 1. So this is another important relation for P naught by P. Okay, then we have next relation as rho naught by rho, which will become T naught by T power 1 by gamma minus 1, because gamma gamma will cancel out. Okay, so sorry, 1 by gamma minus 1. This is another important relation which will be required for analysis of the compressible flows. Okay. Now we can also do one more thing. While we are actually analyzing the flow situation, we can consider that how much ratio of bulk velocity, bulk kinetic energy divided by the molecular motion is actually accounted. Okay, so if I write bulk kinetic energy, that will be V square by, okay, what about molecular motions? If I have to account for molecular motions, then I will be having internal energy U, because internal energy is contributed due to the molecular motions only. So I can write this as V square by 2 divided by Cv into T using the calorically perfect gas. Then from here I can say that V square by 2 Cv I can replace with R by gamma minus 1 times T. So this will become gamma minus 1 by 2. I have to over here multiply and divide with gamma. So if I multiply and divide with gamma, I will get one gamma over here, and this gamma RT will form a square. So V square by a square will be, sorry, Mach number square. Okay, so this is another interesting finding, that whatever the bulk kinetic energy we are having per unit molecular motions actually is nothing but directly proportional to the square of the Mach number. So it means that as you will keep on increasing the Mach number, your bulk kinetic energy will increase with more proportion. Okay, is this one clear for a given flow situation? Now we have initially got one interesting equation which I have numbered equation number 1. Let's try to use this equation to get some more important relations. Yes, so equation was a1 square by gamma minus 1 plus v1 square by 2 equal to a2 square by gamma minus 1 plus v2 square by 2, and this is nothing but the alternate form of the energy equation only. Okay, so let's once again take this energy equation. So if I take this form of energy equation, then what I am getting, a1 square v1 square upon okay. So now if we consider this corresponding to star parameter, what I will get, my initial point is having say speed of sound a and flow velocity v, and then this process I have adiabatically changed such that I am getting a Mach number situation of 1. So corresponding to this I will get that my velocity will be speed of sound will be a star, and corresponding velocity will also be a star. Then only I will get the corresponding Mach number situation as 1. Okay, so if I apply energy equation from these starting points to these final points, what I will get, a square by gamma minus 1 plus v square by 2 equal to a star square by plus, okay, because this corresponding to Mach number, flow velocity has to be a star. Okay, so then from here I can take a star square common, and inside I will get 2 plus gamma minus 1 divided by 2 times gamma minus 1. Okay, and ultimately I will get that a square by gamma minus 1 plus v square by 2 equal to a star square times gamma plus 1 divided by 2 times gamma minus 1. Okay. So now this is important point. So earlier what you were supposed to do? Earlier you were supposed to know the temperature. Okay, T star. But T star is something which is difficult to calculate. Okay. So what we have done now, the easiest form we have obtained is A star we have directly related with the speed of sound and the given flow velocity conditions. Okay. So for given flow velocity will be known to us V, and corresponding to the given situation, say pressure and temperature is also known to us. So corresponding to that speed of sound we can calculate. So from here I can actually predict the value of A star. Okay. Now this relation of A star will be very much important, as I before told you that when Mach number becomes infinity, then M star becomes actually finite parameter. So let's try to make an attempt to find V star. Sorry, M star. So how to find M star? Let's see. I will first write this equation on the next page. So what I am getting, A square by gamma minus 1 plus V square by 2 equal to gamma plus 1 divided by 2 times gamma minus 1. Okay, so this is the relation. So now if you have to make this Mach number, what you have to do? We have to divide this equation with V square. If I divide with V square, then this will become 1 by Mach number square. Okay, so let us divide this entire equation by basically 1 by V square. I am multiplying to this. Okay, so if I do so, I will get gamma plus 1 divided by gamma minus 1, and 2 is also coming over here. Okay, so this A square by V square has become 1 by Mach number square times gamma minus 1 plus 1 by 2 equal to, sorry, this I can write directly as M star or even 1 by M star. Okay, 1 by M star square gamma plus 1 divided by 2 times gamma minus 1. So now this is one important relation which is representing your Mach number with M star. So Mach number of the flow we have now connected with the M star. So from this equation, let's attempt to find the value of M star. So if I have to calculate M star, what I will do first, let me take over here this as 2 plus Mach number square into divided by this will become equal to 1 by gamma plus 1 divided by 2 times gamma minus 1. So 2 will cancel, gamma minus 1 will also cancel. So from here I can get that my M star square, have I done this correctly? Okay. So I will get M star square is equal to gamma plus 1 M square divided by 2 plus m square. Okay. Now let's do one thing. In order to further simplify this, let's divide right hand side by m square. Okay, both numerator and denominator. So my m star square will become gamma plus 1 divided by 2 divided by m square plus gamma minus 1. Okay. So this is one important relation. Now we are representing the star Mach number with the uh, Mach number of the flow. Okay, so characteristic Mach number with the local Mach number of the flow field. Okay, so now what will happen? What will happen? We will see over here that when Mach number is less than 1, we have already seen, we call the flow to be subsonic. When Mach number is equal to 1, then flow is sonic, and when Mach number is greater than 1, then we say that supersonic. Okay. So from this equation, we will find that when my Mach number is less than 1, then m star is also less than 1. When Mach number is greater than 1, then my m star is also greater than 1, and corresponding to Mach number of 1, m star is Mach number is 1, then m star is becoming 1.
m is equal to 1, sonic के सामने m star is equal to 1.
Sorry, okay. Okay, so that is what I am getting over here. From this equation, I can see that the way in which my local Mach number is varying, similarly the characteristic Mach number is also actually changing. However, one interesting fact is that when our Mach number is as high as it approaches to infinity, corresponding to that, you are getting your m star as square root of this 1 by infinity will become 0. So square root of gamma plus 1 by gamma minus 1. So this is a finite value. Okay. So this is actually important. Here the role of m star comes. So for majority of the Mach hypersonic flow situations, when your Mach number is very high, it can be regarded as high as infinity. Okay, because infinity is a relative term. So for certain situation, if it is reaching to some number which is very high in comparison to the other numbers involved in the flow field, then that will become identical to infinity. Okay, so when your Mach number becomes infinity, corresponding to that our characteristic Mach number actually reaches a finite value. So it means any conclusion if you have to make based on the Mach number, that particular conclusion now I can actually make using the characteristic Mach number. Okay, so that is where it will be helping me out. Another important point is, so we have seen this energy equation A1 square by gamma minus 1 plus 2 equal to A2 square by plus. Now this particular energy equation can also be related with the stagnation flow conditions. Okay, so when if I apply this to stagnation flow situation, say initially I was having condition A and V, and finally my condition will become A naught and V naught will be 0. Okay, so if I do apply this energy equation,
hypersonic Mach number तो like 5 to 10 में के बीच में होता है, तो infinity के अंदर भी फिट
what I said, I have not told you that we will be considering infinity. What I am saying is that whenever we are having the relative terms, okay, in certain situation when we have the relative terms. Okay, for example, your other parameters are very small in comparison to that number, so that can be considered as very large quantity. So that is the thing. Okay, and basically whenever you talk about the Mach number for hypersonic flow, you are referring to only the uh, free stream Mach number. You are not having any idea about what are the corresponding local Mach numbers. Okay. Okay, so now if I apply this particular energy equation over here, then what I will get? A square by gamma minus 1 plus v square by 2 equal to a naught square by gamma minus 1. So from this, let's now attempt to find the value of a naught by a. So if I have to calculate a naught by a, let me divide this entire equation by a square. So what I will get? 1 by gamma minus 1 plus v square by a square equal to a naught square by so from here I can say that a naught by a square can become, if this gamma minus 1 get multiplied over here, it will become 1 plus v square by a square will become Mach number square of Mach number. So this is another important relation, that your speed of sound corresponding to the stagnant flow situation and the given local condition is becoming actually proportional to square of Mach number. And from our formulation of speed of sound, we know that for a thermally perfect gas, speed of sound is equal to square root of gamma RT. Okay, so I can write this ratio as nothing but equal to T naught by T. Okay, so this can be also written as T naught by T. If this is T naught by T, then accordingly I can also write the corresponding values for P naught by P, and so my P naught by P will become 1 plus gamma minus 1 by 2 Mach number square and whole power gamma by, okay, and when I have rho naught by rho equal to 1 plus gamma minus 1 by 2 Mach number square times gamma by gamma minus 1. Okay, so today, like you will be seeing, I am driving lot of equations. So basically all these equations we will be utilizing when we are going through the analysis of normal shock waves. So majority of these equations will be utilized, and ultimately if you see, these are nothing but all are the alternate forms of energy equation, because whenever we are starting, always at the starting point we are considering the energy equation, and then we are doing some sort of algebraic manipulations to bring out the more parameters. Okay, so all these alternate forms of energy equations are actually very much relevant for our nothing but the actual analysis. Okay, now one more analogy I can make over here. Let me see. Okay, let me do one thing. I have derived one relation that a1 square by or a square by gamma minus 1 plus v square upon 2 equal to a star square. Tell me the relation. What was the relation? A star square gamma plus 1 2 times gamma minus 1. Okay.
Last two equations, I think there is, it could be gamma minus 1 upon gamma and gamma minus 1.
Where?
The relation.
Relation, let me see from here. Oh, sorry, gamma minus 1 by 2. Yeah. But I have written gamma minus 1 by 2.
No, power. Gamma minus 1 upon gamma.
No. It will be gamma upon gamma minus 1. So this is P by P naught. This is correct. Okay. This is correct. Okay. So this is one relation which represent this left hand energy content in terms of this star term over here. Then just now one relation I have written where this same left hand energy content can be written as A naught square by gamma minus 1. So it means this is the same parameter left hand side, so I can write this simply as A naught square by gamma minus 1. So from here I will get the relation that A star square by A naught square, gamma minus 1 will cancel out, 2 divided by gamma plus 1, and this must be equal to T star by T naught. Similarly, I can find out P star by P naught as whole power gamma by gamma minus 1 and rho star by rho naught equal to one by gamma minus 1. Okay. Now, if you see all these equations corresponding to the room temperature conditions, we will be having value of gamma as 1.4. So for air standard conditions, gamma is 1.4. Corresponding to this, can you tell me how much is T star by T naught? Please tell me these numbers. So first we have to calculate 2 by gamma plus 1. So 2 by 2.4. 0.833. What about second number? Now we have to calculate its power as gamma by gamma minus 1. Point 527. Okay, next number. Point 0.63. So these are three important numbers, but these are valid only for air standard conditions. When you are having air as working fluid at standard pressure and temperature, corresponding to that its gamma will be 1.4 and ratio of its T star by T naught, so characteristic parameter divided by stagnant parameter is actually becoming 0.833, 0.527 and 0.63. Okay, so whatever we have done today, that is nothing but just algebraic manipulation of the energy equation. Okay, so today we have tried to see all the possible forms of energy equation which will be relevant for the compressible flow situations. Okay, so now whenever I will be using this energy equation during my subsequent course, I will not go into the full derivation of, I will just say let's recall that equation from that lecture and this is the relation. Okay, so we will be now directly using all these relations. So from our next lecture we will specifically start with the flow analysis for normal shock wave, and when we will be using the normal shock wave analysis, then all these relations will be very much beneficial. Okay.